Hello everyone. In this video, I'll talk about a question that is commonly asked in digital design interviews. The question is, how do you safely transfer a pulse from one clock domain to another clock domain? Let's first understand the problem in detail using a graphical representation. In this figure, the source clock domain operates with clock CLK1 and the destination clock domain operates with the clock CLK2. The two clocks CLK1 and CLK2 may run at different frequencies. CLK2 may be faster, slower, or even same as CLK1. Now suppose a pulse is generated in clock domain CLK1 and we need to transfer this pulse safely to CLK2 domain while preserving its nature as a short pulse. Here, we assume that the pulses in the source clock domain are sparse and are well separated in time. In order to transfer this pulse safely, we can follow a three-step method. First, convert the pulse into a level signal in the source clock domain. Then synchronize this level signal to the destination clock domain CLK2 using two-flop synchronizer. And finally, regenerate the pulse from the synchronized level signal in the destination clock domain CLK2. Let's look at these steps in detail, starting with the operations in the source clock domain. In this clock domain, we convert the pulse into a level signal. As shown in the figure, let's say there is a signal called pulse underscore n, which stays high for one clock cycle. We sample this signal and generate an output signal level underscore out, which toggles its state every time a pulse is detected. To do this, the signal pulse underscore n is checked at the every rising edge of CLK1. If the pulse is 1, the level out signal toggles. Otherwise, it retains its value. Here is the Verilog code that implements this functionality. Now that we have converted the pulse into a level signal in source clock domain, the next step is to safely transfer this level signal in the destination clock domain. Since the source clock CLK1 and destination clock CLK2 are asynchronous, meaning their edges are not aligned, directly sampling the level underscore out signal in destination clock domain can lead to metastability. To avoid this, we use a two-flop synchronizer. Let's understand this visually using waveforms. The box shown here in pink summarizes the operations performed in the destination clock domain. Suppose the level signal entering the destination clock domain is level underscore n. The first flip-flop in the synchronizer samples this level underscore n signal and produces an output sync underscore ff0. Because level underscore n is not aligned with the destination clock edge, the output sync underscore ff0 may become metastable for a short duration. However, by the next clock edge, it would typically resolve to a valid logic state, and then the second flip-flop in the two-flop synchronizer captures its stable value, producing a clean synchronized output signal labeled here as sync underscore ff1. So by using a two-flop synchronizer, we can safely transfer the level signal generated in source clock domain to destination clock domain. Now comes the final step, converting the synchronized level signal back into a pulse. To do this, we take the synchronized signal sync underscore ff1 and delay it by one clock cycle to generate a new signal called sync underscore ff1 underscore prev. By taking the XOR of these two signals, the original pulse pattern is created in destination clock domain. Each time sync underscore ff1 changes, the XOR of these two signals produces a one clock cycle wide pulse, effectively regenerating the pulse. Here is the Verilog code to implement this functionality. So these are the three steps to safely transfer a pulse across clock domains. That is, by converting a pulse to a toggle signal, synchronizing it with a two-flop synchronizer, and regenerating the pulse back in destination clock domain. This is all for this video. Hope this is helpful.